All right, so this will be the third midterm exam review, the last one that's really long. Final exam will be next week. We're broken up into 3 sections, so there won't be a really marathon section like this. If you haven't been in one of these before, welcome, and also just if you're here live, which is not many of you, feel free to stop with questions anytime, whether it's on the specific problem I'm doing or anything related to that topic. If you can, please wait till I'm finished going through the question, because sometimes I'll answer your question preemptively. So it's just better to wait till I'm finished, and then you can ask for any clarification on what I talked about, or anything, as I said, that's on the same topic, but maybe it wasn't exactly covered in that question. All right, so we'll get going right away with the first one. And so if you recall, the organization of this exam is chapters 7 and 8, and then a little bit of 9, the first 4 sections of 9, which end with phase diagrams. And the exam does roughly go in that order. So what we have here first is material from chapter 7, which dealt with energy, heat, enthalpy, things like that. So the first one is calculate the work when a sample of N2O expands from 3.75 to 8.25 liters against a constant pressure of 957 torr. So whenever you see a problem that asks you to calculate the work, there's really only one equation to worry about, and it's pretty simple. It's that the work is going to be equal to the negative external pressure times the change in volume delta V. So it's just 2 terms you have to multiply together. The only thing to be careful about when you do problems like this, as is true for a lot of problems in this section, are the units. So we see here that all the answer choices are in units of liter atmospheres. So that tells us that we want our pressure to be in atmospheres and our delta V, our volume change, to be in liters. So in this problem here, we're told that we're expanding against a pressure of 957, and that's torr, so we need to make sure we convert to atmospheres first. So our external pressure in the correct units, something we didn't technically learn until chapter 8, but now is sort of combined with this problem here on chapter 7 material. We have a pressure in torr, and we just need to convert to atmospheres by dividing by 760. So 1 atmosphere is 760 torr, which is the same as 760 millimeters of mercury. And in this case comes out to 1.26 atm atmospheres. All right, so that's the number we're going to use for external pressure. And then for delta V, it's going to be final minus initial. So you have to remember that there's a minus sign out front here, and then the sign of delta V is then going to determine whether the work term ends up being positive or negative. So here we're going from 3.75 to 8.5 liters. So the final volume is 8.25. Volume is getting bigger in this situation. And it's starting at a volume of 3.75 liters. And so when we multiply those across, we get minus 5.67 liter atmospheres. So the key mistakes that people make on this problem, in addition to units, are leaving out this minus sign there. That's important to get the sign correct. If it's doing expansion like we are here, that means the system is doing work against the surroundings, and the work would be negative like it should be, so choice B would be the correct one. The only other thing to keep in mind with problems like this, which didn't come up here, is that sometimes we'll ask for the answer in joules, which is the more common unit, I would say, for work and energy. And so you have to remember the conversion factor, that 1 liter atmosphere is 101.3 joules. Now, as I've said before in class multiple times, you might think that, oh, this is just another random conversion factor I have to remember, as if I don't have enough to remember already, but that one you can get from the periodic table. So we've talked about this now in different contexts, but we have, I have to zoom in a little bit so you can see it. Eventually, there we go. All right, so if we zoom in, we see that we have these 2 different values of R, the universal gas constant. One of them is in liter atmospheres, and one of them is in joules. So if you divide those 2, that will give you that 101.3 joules per liter atmosphere. So you can, if you forget that number, you can just get it from here by dividing these 2 numbers. All right, so any questions on that problem or that topic? All right, on to the next one then. In number 2 here, we're talking about what is the change in internal energy in kilojoules when a system absorbs 965 joules of heat and has 456 calories of work done on it. 1 calorie is 4.184 joules. So if we take it one step further now, this is a problem that's asking about the change in internal energy, not just the work part. And so remember that this is going to be abbreviated as delta E. And if you see a problem that asks you for that change in internal energy and it involves heat and work, again, it's a pretty simple relationship that we have to keep in mind, which is that delta E is just going to be the sum of the two, Q plus W, where Q is the heat and W is the work. In this problem, because we're adding two numbers together, they need to be the same units before we can add them. And the other thing that's important is the sign conventions for Q and W. They can be positive or negative. And in many cases, like we have here, it's not going to be explicitly stated in the problem whether it's a positive or negative number. A lot of times it's going to be given to you in sort of a word format where you have to assume the sign correctly based on how it's described. All right, so that's going to be the case here. We want the answer in kilojoules, and so we'll probably want to put Q and W in either joules or kilojoules to start with and then convert. So the first thing we have is the heat term here, Q. And we're told in the problem that the system absorbs this much heat. So whenever heat is absorbed, what does that mean about the sign? Is it positive or negative? Positive, that's great. So it's going to be plus 965 joules. Absorbing 965 means that Q is plus 965. And then the other one is the work, which is W. And here we say work is done on the system. So does that make it positive or negative? So the two options are done by the system, done on the system. If it's done on the system, that's going to be giving energy to the system, so that would be a positive contribution to the overall delta E. So when work is done on the system, it's going to be positive, and here it's given as 456 calories. If we're going to add it to the Q, we need to be in the same unit, and we're told here that the conversion factor is 4.184 joules in 1 calorie. And so in total, that W work term is going to be 1908. And so now we have them in the same units, so we can add them together. 965 joules for Q, positive 1908 for W. Both of them are positive in this case. That gives us 2,873 joules, which in kilojoules, just dividing by 1,000 is 2.87 in the correct number of significant figures. All right, I guess choice A then would be the one that works out for this. All right, so most of the other answer choices would have involved getting the sign of one or both of those terms incorrect. So when you have heat is absorbed is going to be positive, heat released would be negative, work done on is positive, work done by would have been negative. So make sure you pay close attention to the wording and keep those conventions straight when you do problems like this. Any questions? All right, so the next one here is a conceptual question dealing with, exothermic, which refers principally to delta H, another sort of related term for change in energy that's a little bit differently defined, as we know, but means similar things and used a lot in chemistry context. So here we have a reaction between hydrochloric acid and sodium hydroxide, which is exothermic. So which of the following statements about this process is correct? So let's just sort of analyze all of them. All we know about this is that it's exothermic. It's the only thing we know. So the first choice A deals with the sign of delta H. So we have to remember the terminology here. Whenever it's exothermic, is delta H going to be positive or negative? I heard a negative. You guys are being shy today, but that's all right. You can say it. There's no judgment here. All right, so exothermic, we're talking about a negative delta H. So this one would be incorrect. If it was endothermic, it'd be positive, but exothermic is negative, as we're dealing with here. For choice B, this is the one that sometimes is a little bit confusing to think about because we don't always define delta H in this way, even though it can be thought of as this. So the enthalpy of the products are greater than the enthalpy of the reactants. So even though we don't calculate delta H this way, remember that anytime we have a delta in front of something, that means the change, or that means final minus initial. So when you're talking about a chemical reaction, the final state is the products, the initial state is the reactants. And so if you're talking about delta H, it's going to be the difference between those two, products minus reactants. Again, we don't typically calculate it this way because it's hard to define absolute enthalpy of reactants and products. But if we could do it this way, and this is how you can think about it anyway. And so products minus reactants is delta H. Now we know because it's exothermic that this has to be 0. And so in order for this to be 0, or sorry, less than 0, not 0, negative less than 0, that means we're subtracting a bigger number from a smaller number, which means that the products have to be less than the reactants. So when you have an exothermic reaction, the enthalpy of the products is less than the enthalpy of the reactants. That makes products minus reactants negative, less than 0. And this one says that the enthalpy of the products is greater, so that one is also stated incorrectly in the opposite order. Okay, so whenever you have an exothermic reaction, think about it in this way, and to get a negative number, you need to have a bigger number subtracted from a smaller number, so reactants are bigger than products. All right, for choice C here, the temperature of the surroundings increases. So whenever we have a change in internal energy, a delta E or delta H, which is closely related, you're always going to have energy transferred between system and surroundings in the form of heat and or work. And so that's always going to be true. And so when you have an exothermic process where you're transferring enthalpy or heat in some way, so exothermic means that heat is released from the system. And so if heat is released from the system, it goes into the surroundings, and if heat then goes into the surroundings, the temperature of the surroundings will go up. So anytime you have an exothermic process, your temperature of the surroundings increases. The classic example will be burning something. If you do a combustion reaction, delta H is always very negative, and that obviously is exothermic. And when you burn something, of course, heat is released like crazy. So that's a way to think about that and remember it. So you have an increase in temperature of the surroundings. So this one looks to be correct. Let's verify that D and E are incorrect. It's good to go through all the answer choices to make sure. Here we say the bonds in the products are weaker than the bonds in the reactants. So this is one where we have to think about one of the other ways we learn to calculate delta H, which is taking bond energies of the reactants and products and then subtracting them. And remember, when we do it that way, it's going to be reactants minus products because of how bond energy is defined as a breaking of a bond. So when we calculate delta H in this way, and there may be I think there's a numerical problem that uses this later on, so we'll see it again. When you calculate delta H in this way, it's the sum of the bond energies of reactants minus those of the products. And again, we're talking about an exothermic process here, which is less than 0 for delta H. And so that means, again, if you're less than 0, that means you're subtracting a bigger number from a smaller number, which tells us that the products must have stronger bond energies than the reactants. This sum here must be bigger than this one in order for the difference to be negative. So this tells us here that the sum of the bond energies for the reactants is smaller than that of the products, or products is bigger than reactants, however you want to write that out. And so here it says the bonds are weaker in the products, but that's, again, the opposite of what should be true. Whenever you have an exothermic reaction, you're forming stronger bonds in the products, which is why this number is bigger, and the difference would be negative. All right, finally, last one, choice E to go through. The reaction absorbs heat from the surroundings. As we kind of already said in analyzing choice C, if you have an exothermic reaction, that means the heat is negative. It's, delta H is a heat term measured at constant pressure, and so when you have a negative heat, that means heat is released. So it would be absorbed if it was endothermic, but released if it's exothermic. So this one is also incorrect, just to verify. So choice C is the only one that checks out correctly for an exothermic process. And basically, if it was endothermic, everything would just be opposite of what I said here. So that's just the key distinction between them in terms of the sign of delta H and then the relative enthalpies and bond strengths and things on reactants and product side. All right, so any questions on that or any of the other concepts dealing with delta H? All right, on to number 4 then. So here we have, and we didn't do a lot of problems exactly like this in class, and so this one is a good one because it goes over a problem type that we didn't see a lot in class, even though there was some kind of like this in the homework assignment, and it combines concepts from chapter 8 and chapter 7. I don't know that there will be an exact question like this on the exam that requires you to sort of dig from both things from chapter 8 and chapter 7, but this is a good one for review at least because it allows us to see that. All right, so we have a combustion equation here, and it's called a thermochemical equation because it has the balance equation and the delta H. It seems like people are struggling with that door for a lot of people trying to break in. All right, so this is the thermochemical equation we're given. So Again, the coefficients tell us how many moles of each substance are involved, just like they would for any chemical equation, and then delta H tells us the change in enthalpy when that many moles of substances react or are formed as products. So what we want to know here, though, is what is the enthalpy change when 12.5 liters of ethane, C2H6, measured at 25 degrees Celsius and 780 torr, is burned in air? Give your answer with 1 decimal place to no units. Okay, so this is what's the way we treat these problems is essentially like a stoichiometry problem, where we know that the delta H tells us that enthalpy change is negative 2,855 kilojoules when 2 moles of C2H6 burns, and we want to figure out what is delta H when this amount of C2H6, 12.5 liters at this temperature and pressure, is instead burned. Let me see if those people want to come in. They might not know there's a second door. All right, well, they're gone. I hope their persistence in studying for the exam is more than their persistence in getting into the room. All right.
They were maintenance people.
Oh, they were maintenance people. I couldn't see them. All right. Thank you for clarifying that it wasn't students that I'm keeping out. All right. All right, so we have this problem here. So what we're going to do for this is when you approach a problem, basically it becomes stoichiometry. We're going to figure out how many moles of ethane are we actually burning, and then we're going to relate that to the thermochemical equation, which tells us delta H for 2 moles of ethane, using it as a conversion factor. So the first thing we need to do, just like any other stoichiometry problem, is find moles. Now again, the more common way might be to be giving you the mass of the product or something like that we've used before, but in this question we're giving you volume, temperature, and pressure, which we're going to use then the ideal gas law for. So because C2H6, all of these are gas phase reactions and products, as it turns out, we can use PV equals nRT to relate the given information to the number of moles that we have. Now, in order to use PV equals nRT, we need to have atmospheres for our pressure. So that's another conversion we're going to have to do again. Chemists like using torr, even though the ideal gas equation uses atmosphere, so it's kind of annoying, but we have to do that. So we have 780 torr. We've already done this conversion once. 1 atmosphere is 760 in torr. So it's not much different than 1 atmosphere. It was 1.03. And so with that pressure in the correct units, now we can calculate N, which is the number of moles of C2H6. So we're going to just rearrange this. It's going to be PV over RT. And so the pressure is 1.03 atmospheres. We have 12.5 liters. And then we have R in the denominator, which is going to be the one that we use for gases, 0.0821. That number is on the periodic table, so if you forgot it, it's there. And then the temperature needs to be in Kelvin. 25 Celsius add 273 is 298. We see that one all the time. All right, so we're going to put that in, and we get 0.526 moles of C2H6 that we're burning. And so now we know that we're burning this many moles of C2H6, and using the delta H in the balance equation, we can figure out then the enthalpy change corresponding to that amount of C2H6. So for our delta H, we're going to have, again, exactly like a stoichiometry problem, 0.526 moles of C2H6. We find moles first. And then we can almost treat this negative 2,855 delta H value as another product for the reaction. So delta H is minus 2,855 kilojoules, and that's going to be the enthalpy change when we burn 2 moles of C2H6 because there's a coefficient of 2 there. So a lot of people might just multiply these two numbers together, but in this thermochemical equation, delta H corresponds to 2 moles of C2H6 because there's a coefficient of 2 in front of it there. So I'm going to put a 2 down here. So that cancels out moles and gets us an enthalpy change in kilojoules. That's going to be our final answer, minus 750.9. In Blackboard, of course, you would just enter that and be done. Okay, so this is a thermochemical equation problem where you're treating it a lot like stoichiometry. Find moles of substance and then relate moles of substance, whether it's a reaction or a product, and to delta H using the delta H that's given to you and the coefficients that are in front of whatever substance you're dealing with. Okay, so any questions on that? All right. Another major topic in Chapter 6 was heat transfer and calorimetry, where we use the equation mc delta T quite often. So here what we're doing is we're taking 5 grams of copper metal with a given specific heat capacity of 0.385 joules per gram degree Celsius. We're heating it to 100 degrees Celsius. Then we're placing it into 10 milliliters of water, which is initially at 23 degrees Celsius. What would be the final temperature in degrees Celsius, assuming no heat is lost? All right, so in problems like this, we have heat transferring between one substance and another. And it's just a physical process. There's no chemical reaction happening. We're just taking a piece of metal and putting it in water. So it's not a situation where we have a chemical reaction occurring. But the way that we would do this is we would say that the heat transfer, so the heat for one substance, which in this case is copper, is going to be equal and opposite to the heat for the other. So we can put the minus sign on either side. Doesn't matter where that goes. We have to recognize that if one substance is at a higher temperature and is releasing heat to the other substance is going to be gaining that heat. So the signs of the two heat terms will be opposite for the two, for whichever one starts out at the highest temperature, whichever one starts out at the lower temperature. And so we need a minus sign on one side if we're going to set them equal to each other. In this case, we don't have to worry about, we're placing it into a cup, but we didn't tell you anything about the heat capacity of the cup, so we don't have to worry about heat being transferred to that. We're just assuming here that heat is transferred only in between the piece of copper that we're putting in and the water that's in there. So what we then basically do in this is we're just going to use for each side of this equation mc delta T, where m is the mass of each substance, c is the respective heat capacity, and then delta T is going to be the change in temperature. All right, so what we have then to rearrange this is the mass of copper, heat capacity of copper times delta T for the copper is equal to negative mc delta T for water. Again, it doesn't matter which side the minus sign goes on, but it needs to be there on one side of the equation. And in this case, our unknown is going to be the final temperature, because, and remember, for each substance, the delta T is the final minus the initial, and that final temperature is what we're solving for here. And the key concept to that to realize is that the heat transfer stops when they get to the same temperature. So the final temperature, TF, is going to be the same on both sides. Basically, once the copper gets to that temperature, once the water gets to that same temperature, that's when the heat transfer stops, and that's where we're trying to figure out where that occurs. So now we just have to start plugging in numbers onto each side of the equation. So the mass of copper is 5.00 grams. The heat capacity of copper is given as 0.385. And then our delta T is final minus initial. So TF, final temperature, is our unknown. The initial temperature for copper is 100 degrees Celsius. And then on the other side, we have the mass, a negative sign out in front, mass of water. So 10 milliliters of water is equivalent to 10 grams. The density of water is 1. So if we give you the number in milliliters, it's the same in grams. The only heat capacity we expect you to know is the heat capacity of water. I didn't check all the exam questions. I think we give it to you sometimes, but I'm not sure if it's there in every problem. So make sure you're familiar that we've used it a lot, so you should be already. 4.184 or 4.18 is enough if you just want to remember that. Joules per gram degree Celsius, and then same final temperature, TF for water, is the same as copper, and then the initial temperature for water was 23 Celsius. I did a bad job of spacing it out, but there you go. So those are the numbers on each side. 5 grams times the heat capacity, 0.385. Delta T is, for copper, is final temperature minus 100. Mass of water, heat capacity of water, delta T for water, over here written as final minus initial again. All right, in the interest of time, I won't do all the algebra, but you're just going to have to, the whole left side of the equation is, you just have to distribute the terms. So multiply these two together and then distribute. Same on the other side, and then combine all the like terms to solve for your unknown. So what we get is our final temperature should be 26.39. They want to do 2 decimal places here, so just follow the directions in Blackboard, and that would be the number we enter in. So when you do problems like this that involve heat transfer between two objects and solving for the final temperature, your final temperature needs to be in between the two starting points. So copper's at 100, water's at 23. So you need to get a number that's in between those two values. If you don't, that means you made a math mistake somewhere, and it's good to check yourself. So, any questions on that? All right, so on to the next one then. This one here is a more typical calorimetry problem. We're doing a chemical reaction in a calorimeter. And here we're talking about a bomb calorimeter, which that terminology is not terribly important for doing these problems. So that just means a enclosed constant volume calorimeter, commonly used for combustion reactions. So here we're giving you the heat capacity for the bomb calorimeter by itself, which is 9.25 kilojoules per Kelvin, and it's filled with 1.00 liters of water. We take a 5-gram sample of acetic acid, which has this molar mass, burn it in the calorimeter, and the temperature raises by 5.40 degrees Celsius during the process. Using all this information, determine the enthalpy change for the combustion of acetic acid. And again, the equation here given below for 1 mole of acetic acid. All right, so in problems like this, what we essentially do is three key steps. One of them is very trivial, but what we're going to always start with in calorimetry problems is calculating the heat for the calorimeter. And that's going to be coming from heat that's absorbed by the water in the calorimeter plus the heat that's absorbed by the calorimeter itself. And this is one of those situations, again, where which of these two terms we use depends on the information we're given. So we can expand this out a little bit further and say that the heat for the water in the calorimeter is still MC delta T, just like we calculated in the last one. And then the heat absorbed by the calorimeter is the heat capacity of the calorimeter times delta T, where this is a specific heat capacity for water per gram. This is just the overall heat capacity for the calorimeter. And in problems like this, you just have to look at the information that you're given to decide if I'm going to use one of these two terms or both of them. So in this problem here, we're telling you that there's 1 liter of water in the calorimeter. So that tells us how much water is in there. So we have enough to do this term. And we're also telling you that the heat capacity of the bomb calorimeter itself is 9.25 kilojoules per Kelvin. So we have this information as well. So this is when we're going to use both terms to calculate the heat for the calorimeter, using the amount of water that's in there and as well as the heat capacity of the calorimeter itself. A common mistake that people make in these problems is using this mass to calculate heat. This is the amount of substance that we reacted in the calorimeter, but it's not the amount that's absorbing any of the heat. It's just the amount that was burned. So when we're using MC delta T to calculate heat, or part of the heat term as we're doing here, it's always the mass of the water that's in the calorimeter which is absorbing the heat, not the mass of the substance that we're burning or reacting. All right, so with that in mind, we can now calculate this first part. The heat for the calorimeter is going to be the mass of water. We want the mass in grams because the heat capacity for water is in joules per gram Kelvin. So we have 1 liter, which is 1,000 milliliters or 1,000 grams. So you have 1,000 grams of water, heat capacity of 4.184. And then our delta T, we're saying that we're raising the temperature by 5.40 degrees Celsius, so delta T is a positive 5.40. And then we're going to add to that the heat capacity of the calorimeter. So we have to be a little bit careful, though, because we want our final answer to be in kilojoules per mole, and this second term here is also going to be in kilojoules because that's how we gave you the heat capacity for the calorimeter. So before we can add these together, they need to be both in kilojoules, or at least both in the same unit. So let's convert that right now so we don't forget. 1 kilojoule is 1,000 joules. So we're kind of doing a little bit of a shortcut here, but this term will be in joules because of the heat capacity of water being in joules. We divide by 1,000 to get it to kilojoules before we add it to the other one. And then the second term here is going to be 9.25 kilojoules. Now it's given as per Kelvin, but remember for heat capacities, because it's in terms of delta T, Kelvin and Celsius are interchangeable. So we can write that as 9.25 kilojoules per degree Celsius, same temperature change, 5.40. The whole calorimeter, the water and whatever the container is, are going to have the same delta T as the reaction takes place and as the temperature equilibrates. So when we add these all up, we get 72.5 kilojoules, provided that we did everything correctly. All right, so that's the step. That's sort of the first step, calculating heat for the calorimeter. The second step is trivial, which is just to recognize that in a calorimetry situation, the reaction that you're studying is the system, and the calorimeter is the surroundings. As we talked about a little bit before, whenever you have heat transfer, it goes from system to surroundings, which means it's going to be the same in magnitude, but opposite in signs. So the heat for the reaction that we're studying is just equal to the negative of the heat for the calorimeter. So it's going to be negative 72.5. The temperature of the calorimeter is increasing. That's telling us that it's a exothermic reaction, so the heat for the reaction should be negative. Moreover, we're telling you that we're burning something in here, so burning is always going to be exothermic, as we know. And then finally, the last step here is this heat for the reaction is the delta H when we burn 5 grams of acetic acid, but what we're looking for as our final answer is the delta H for the combustion reaction that involves 1 mole of acetic acid, because it has a coefficient of 1 in front of it. So what we have to do then is we have to find delta H for this reaction by taking the heat of reaction that we just found and then dividing it by the moles of substance that we're burning, in this case acetic acid. So it's that number, negative 72.5 that we found, divided by moles of the substance. So the amount we're given here, we're burning 5 grams, that's where that number comes into play. So we need to convert that to moles first. So the moles of acetic acid, 5 grams, and then we divide by the molar mass to get it into moles, just like we did all the time starting in chapter 5. Okay, so 1 mole of acetic acid has a mass of 60.02 grams. That's what the molecular weight or molar mass tells us. And so that comes out to 0.0833 moles. So when we divide the heat of the reaction, minus 72.5, by the 0.0833 moles of substance that we burned, what we end up with is a delta H that's minus 870.3 kilojoules per mole, meaning that when we burn 1 mole of acetic acid, this would be the delta H that we got. Okay, so this is a pretty typical bomb calorimetry problem. You're likely to see one on the exam. And it's always going to be these same 3 steps. Calculate the heat for the calorimeter using the given information in the problem. Relate that to heat of reaction, which just means putting a minus sign on it, or changing the sign. And then taking that and dividing it by the amount of substance, typically the moles of substance, how we want it to be done, to figure out delta H per mole. Okay, so any questions on that? One thing to keep in mind to kind of relate things, we did this problem here and then number 4 earlier, which is a thermochemical equation. These essentially are the same concept but in reverse. So in number 4, we gave you the delta H in the chemical equation and asked you to figure out what would be the heat of reaction if we were burning this much substance. This time it was in terms of gas phase, but still a specific amount. Here we did the opposite. We gave you how much substance you're burning, had you calculate the heat of reaction, and then find delta H by dividing the two. So it's kind of going backwards for those two if you were able to recognize that. Yep.
So for the one at the top, were you just plugging in the numbers to the delta H equation?
Which one up?
The one you went to a couple seconds.
Number 4?
Yeah. If you just plug the numbers into the delta H equation?
Well, there's not really an equation here. This one was treated like a stoichiometry problem. So for this problem here, what we did was we used the PV equals nRT to find out how many moles of substance we had, and then we used this here as a conversion factor, which is minus 2,855 kilojoules, delta H for 2 moles of that substance. So moles of substance multiplied by that is sort of like a stoichiometric conversion factor, relating delta H to moles of substance from the balanced equation. So there wasn't really a specific delta H equation here. Down here, what we did was, this was calorimetry, so we used the equations for calculating heat were kind of the biggest sort of first step, and then from there just relating that to delta H by dividing that by the moles of substance, kind of going backwards from what we did before. There will be the next one here, and the next couple will involve calculating delta H in different ways. But here it was calorimetry, where we're going to use the information to calculate heat for the calorimeter and then relate that to delta H in the next 2 steps. All right, other questions? Okay, so for number 7 here, we're asked to calculate delta H of formation for B2H6 using the following data. So this is going to be a Hess's law problem where we're using three given equations, three given thermochemical equations that have balanced equations with delta H values associated with them, and we're going to combine those in some way to find delta H for a different reaction. Now here, though, we didn't tell you exactly what that reaction is that we're looking for. But we told you that we're trying to find the delta H of formation for B2H6. So basically, to remind ourselves what that refers to, the delta H of formation is the enthalpy change associated with forming the compound from its elements in their standard states. So if we want to calculate delta H of formation for B2H6, we're looking for an equation where we're forming 1 mole of B2H6, which is a gas, from the elements in their standard state. So the two elements that make this up are boron and hydrogen. Boron as an element is just B. But then hydrogen, what we have to remember is the standard state for hydrogen is not just H, it's H2 as a gas. So that's the important thing to remember for standard states. And then we have to balance this out. We leave the coefficient on the right side as 1, and that puts us at a 2 there and a 3 there. So essentially what we're asking to do here is we're trying to figure out how to combine these three equations to get this equation here, and then the delta H that we get would be the delta H of formation that we're trying to find. So the delta H for this equation would be the delta H of formation of B2H6. That's what we're looking for. So all we're going to do is typical Hess's law. We're going to take three given equations, 1, 2, and 3, as I'll number them here, and figure out how to combine them such that we get 2 borons plus 3 hydrogens going to B2H6. So we can do this in sort of whatever order we want, sort of piece together the three equations. But as I said, typically you want to look for reactants and products that occur only once in the given equation as well as in the overall equation. And I think that's going to be true for all of them here. So boron only occurs in the first equation. Hydrogen only shows up in the second equation. B2H6 only shows up in the third. So this one should be a pretty straightforward one to piece together. We're going to have a bunch of oxygen that ends up canceling out as well as water if we do things correctly, but we can just go one at a time. So our overall equation has 2 borons, 2B as a reactant. Equation 1 has 4B as a reactant. So to make those match, we have to multiply all these coefficients by 1/2. So we're going to take the first equation and multiply it by 1/2. So that takes all three of these coefficients and cuts them in half. So it's going to be, I'll leave all the states of matter off. That doesn't really matter for these too much. So 2 boron plus 3 halves O2 going to B2O3. And because we multiply the coefficients by 1/2, the delta H that we're given for that also gets cut in half. So it's going to be 1/2 times the first delta H, or minus 1254.6 kilojoules. So that's how we're going to modify the first equation. That ensures that we're getting 2 borons as a reactant, which is what we want for this overall equation here. For the second one, this is where we have to be a little bit careful with coefficients. We want 3H2 as a reactant in this overall equation for delta H of formation. Second equation has 2 H2s. So if we want to make 2 into 3, we have to multiply it by what number? Be 3/2 or 1.5. So we're going to do 3/2 times equation 2 to make sure then that H2 has a coefficient of 3 instead of 2. 3/2 times 2 is 3. So we're going to multiply all three of those coefficients by 3/2. So it's going to give us 3 H2s plus 3 halves O2 going to 3 waters. And the delta H for this, because we multiplied the second equation by 3 halves, is going to be 3 halves times the given delta H. So the given delta H is minus 571.7. Multiply that by 3/2, we get minus 857.6 for the modified delta H. All right, then finally for equation 3 here, we want B2H6 to be on the product side for the equation that we're trying to calculate delta H for. But B2H6 is a reactant in equation 3, so we're going to have to flip the whole thing to put B2H6 over on the right side. So when we flip it, that's equivalent to taking the negative of it. So we're going to flip equation 3, which means all the reactants become products and vice versa. So that's going to become B2O3 plus 3H2O forms B2H6 plus 3 O2s And because we flipped the whole equation over, we're going to just change the sign of delta H. So that third delta H, we just take off the minus sign, and it becomes positive 2,147. Okay, so those are the three modified equations with the correctly modified delta H values. And now we can ensure that they all add up correctly. So our two borons, 2B carries through. We have, for O2, we have 3 halves O2 from equation 1, 3 halves O2 from the modified equation 2, so that's 3 O2s on the reactant side, and we also down here have 3 O2s on the product side. So all of our O2 cancels out. 3 halves plus 3 halves on the reactant side is 3, 3 more on the product side, they all cancel out. We have the 3 H2s that carry through and don't cancel out with anything else. And then our B2O3 from this equation cancels out with the B2O3 from the first one, so those cancel, one on each side of the arrow, and then 3 H2O here on the left side of the arrow in equation 3, the modified form here on the right side, so all those cancel out. And then all that's left on the product side that hasn't canceled out yet is the B2A6. So it's good to verify that you've done things correctly and that they add up, not just necessarily blindly trust yourself. So we verified that these add up together, and that means then that the delta H that we're getting, which is the delta H of formation for this compound, is just the sum of these three modified delta H values. So minus 1254.6 minus 857.6 and then 2147.5. Adding those all together, what I got was 35.3 kilojoules. And I guess technically it's per mole because it's 1 mole of substance being formed. It's typical for delta H. So that would be choice B here, 35.3 kilojoules per mole when we take these three modified delta H's and add them all together. Okay, any questions on that? So that's Hess's law. It's kind of like putting a puzzle together, as we talked about before. You just need to piece together the three given equations to find whatever equation you're looking for to get delta H for that. Okay. All right, and then the next one deals again with enthalpy of formation, which is sort of the other way that we use it. We can use delta H of formation values to also calculate delta H for any other reaction. So here what we have is we're looking for the enthalpy of formation of ammonia, NH3, where we're given that this equation here has a delta H of minus 1134.4, and the delta H of formation for the other substances are 33.2 kilojoules per mole for NO2 and minus 241.8 for gas phase water. So when you see problems like this where you have delta H for a reaction and you're relating it to delta H of formation for a bunch of substances that are in the reaction, that relationship, which we talked about a little bit before, actually we haven't talked about yet today, but sort of similar to something we talked about before, is that you can calculate delta H for any reaction by taking the sum over all coefficients of delta H of formation for the products minus that for the reactants. I'll use different numbers there. So n is just the coefficient, nn are the coefficients on each side. So with this equation, the more standard and perhaps the more common way to use it is we give you the delta H of formation for all the reactants and products, and then you add them up and subtract them to get delta H for the reaction. In this case, though, what we have is we're giving you the delta H, the minus 1134.4 kilojoules is the delta H for the reaction, and we're solving for one of the unknown delta H formation values. So what we have then is, in this situation, delta H is given as minus 1134.4. And that's going to be equal products minus reactants. So on the product side, we have 4 NO2 and 6 H2O. Both of those delta H formation values are given, so we're going to multiply each of them by the coefficients. So NO2 has a coefficient of 4. We're going to multiply that by its delta H formation, which is 33.2. And then we're going to have a coefficient of 6 for water with a delta H formation of minus 241.8. Then we're going to subtract from that the delta H is the formation of the reactants. So on the reactant side, we have NH3. That's our unknown delta H formation. That's what we're trying to solve for, and it has a coefficient of 4. So we're going to have 4 times the delta H of formation of NH3, which we don't know what that is. That's what we're going to find. And then the other reactant, we have 7O2. What's the delta H of formation for O2 gas? It's not given to us, but what is it? Every element in the standard state has a delta H formation of what? 0. So anytime you have an element in your equation, a standard state element, O2 gas, H2 gas, carbon, iron, whatever, if it's an element in a standard state, the delta H formation is 0. So that term there is going to be 0 for O2. So we don't need it, even though it's not given to us. And so then this is, again, this is our unknown value here that we're going to solve for. And when we do the algebra, delta H of formation for NH3 comes out to minus 45.9 kilojoules per mole, which is choice A. All right, so this relationship, delta H of formation of products minus reactants, is going to be useful anytime we're giving you a bunch of delta H of formation values. And really the only two variations on this theme are going to be either solving for delta H of the reaction, or here we gave you delta H of the reaction, asked you to find one of the delta H of formation values that was unknown for either the products or reactants. And always remember then that any elements that show up in these equations, like O2, have a delta H of formation of 0, so that won't be given to you. All right, any questions?
Did you do algebra or to find the delta H of formation of?
Yeah, so what you'll do is, like, this is kind of like, you call this x, I guess. So you have negative 1134 equals this number minus 4x, and then you solve for x, basically. If you were solving for delta H, there wouldn't be any algebra involved. You'd just have all numbers on the right side. But here, you have to do a little bit of rearrangement to get that isolated, yeah. All right, anything else? All right, on to number 9. And then the last way that we have for calculating delta H of a reaction, which we referred to earlier when we were doing, where's this problem? Thought I had this one here. Hold on a second. All right, well, I have to wing this one. I changed some of the questions around a while ago, and I did not include this one. All right, we'll get it. Okay, so what we have here is we're going to use the bond strengths to estimate, whether it states delta E or delta H. They're, remember, interchangeable in this context, so don't worry about that distinction for these problems. But we're using bond strengths to estimate what that value would be for this reaction. So this is the other way that we have for calculating delta H or delta E, using bond energies or bond strengths instead of enthalpy formation like we did last time. So in a problem like this, what we're gonna use is the relationship that the delta H is going to be equal to, and this time it's going to be reactants minus products. We have to remember this distinction between these two ways of calculating delta H. If we're using delta H in formation, it's going to be products minus reactants. If we're using bond energies, bond strengths, which are synonymous with each other, then it's going to be reactants minus products. The other difference with this one too is that we're not going to have just one value for each substance in the reaction necessarily. We have to account for every single bond that they would have, and making sure that we get that right involves sometimes drawing Lewis structures. So if we want to draw these out, COCl2 if we want to complete the octet on carbon, we have to make sure we have a double bond to oxygen there. Okay, so I'm going to go through these kind of quickly because we don't. But if you have any questions about the Lewis structures, let me know. But for COCl2, the first one we have to recognize that there's a carbon-oxygen double bond there, which is necessary to complete the octet on carbon. Put that as a single bond, and that's important because all the different CO bonds, triple bond, double bond, single bond, they all have different bond energies, and so we have to make sure we're using the right one for that side of the equation. All right, H2O is a pretty simple Lewis structure, and you don't have anything besides single bonds to hydrogen, so it's going to be 2 OH single bonds. That's easy enough. And then on the product side, we have CO2. We've drawn that Lewis structure plenty of times, but it is important to remind ourselves for this that it has 2 2 carbon-oxygen double bonds for CO2, and then we have HCl, which is just one bond HCl, but there's 2 of them, so we have to make sure that we account for that. That appears twice. So now what we're going to do is we're going to just do bond energies of reactants minus products. So on the reactant side, probably going to run out of room, so I'm going to make this a map. Anyway, in the first reactant we have a carbon-oxygen single bond, or sorry, double bond. That's the important part. That's a double bond. So that's going to be 1 times 1070. We have 2 carbon-chlorine single bonds. The CCl, CCl. So there's 2 of those, and that bond energy is 339. I have to do my math in my head because I don't have this one written out. And then we have the 2 OH bonds from water. And the OH bond is 467. All right, so that's going to be what we have on the reactant side. And so the sum on the reactant side add those numbers together. Give me a second. If somebody beats me, let me know. Shout it out. So I got 2,682. If anybody gets something different, let me know because I'm doing this on the fly right now. All right. I need to probably give myself a little bit extra room. Sorry about this. Did I put it in the right place? All right, so that's what we get on the reactant side, and then we're going to do the same thing on the product side. A little bit simpler on the product side, not as many bonds. We have 1 CO2 that has 2 carbon-oxygen double bonds, and we're counting up the individual bonds here, not just one for each substance. So CO double bond, CO double bonds, so there's 2 of those. And then we have 2 HCl. So HCl itself only has 1 bond between hydrogen and chlorine, but there's 2 moles in that balanced equation, so we need to still multiply that by 2 because that's happening twice. So 2 HCl's. And that's going to be 427. And so that sum on the product side as we talked about when we introduced these problems, this is more like accounting than chemistry. You're just keeping track of all the bond energies, adding them all up. 2,994. Really hope I'm not making any math mistakes here. Okay, and then finally what we get is for the delta H, it's going to be reactants minus products. That's why I did it in this order. So we have 2,682 for reactants minus 2,994 for products. And I got minus 312 kilojoules. All right, did anybody catch me making a mistake there? Because, as I said, I forgot to write this one out ahead of time and I did it quickly. But it should be, the equation looks like it's balanced. And I think we counted everything correctly. So as long as I didn't make a calculator error, I think this is all right. All right, did anybody catch a mistake? No? Yes, you caught a mistake?
Yeah, the reactants is 2,257 and the products is 2,344.
What did I do? What did I do? What a disaster. Okay, let me check again. 1070 plus 2 times 339 plus 2
Use the
times...
triple bond.
Oh no.
On the reactant side.
That would have been nice to know 5 minutes ago. Oh god. Well, this is why I write out notes beforehand. And I'll try to wing it. Okay. So there are mistakes here. I could pretend like I was doing that on purpose to see if you guys caught me, but that's a lie. All right, so this comes out to, so you got 2357,
2357.
right? And then this one here, oh my god, that's not the double one. All right, this one's doubled. You got 2344.
Yeah.
So this is actually going to be a very small delta H. All right, I made the mistake that I warned you guys not to make. And now we're all good. So it's actually a very small delta H of plus 14. All right. This is what I get for telling you guys not to say anything until after I finish the question. And you just watch me do the whole thing wrong and I have to fix everything. All right, from now on, if I screw up, you're welcome to interrupt me in between. Okay, thank you though for clarifying that, and I think it's right now. So I made the mistake of reading off the wrong carbon oxygen bond. This is the one that we should have used for both sides. On both sides, we have carbon oxygen double bonds. That's the one that's correct. Okay. Any questions on that besides my inability to do math? All right, on to the next one then. We're into chapter 8 now. And so again, these reviews are designed sort of to match the distribution of topics on the real exam. So first 9 questions on chapter 7 material, essentially that's going to be what you'll see. All right, here we have into chapter 8 though, stuff dealing with ideal gases. We have a balloon filled with an ideal gas that has a volume of 253 milliliters at 24 degrees Celsius. What is the volume if the temperature is increased to 86 degrees Celsius? Now we could recognize that this is Charles's law. This is the relationship between volume and temperature. We could then set up the equation that's associated with that and go from there. But if you don't want to remember all the individual gas laws, or if it's a problem that doesn't deal specifically with one of those 3, then we can always just start with PV equals nRT. And we're just going to isolate the variables that are changing. So in this case, we have volume and temperature that are changing. We're not told anything about the other 2, and we're telling you that we didn't say anything. So if we're saying nothing, you assume that they're constant. So we're going to say that pressure and temperature pressure and number of moles are constant, but it's going to be volume and temperature that are changing. So these are the 2 that are changing in this problem, volume and temperature. So we're going to move them over to one side by doing a little bit of algebra. So volume divided by temperature is nR over P. N and R and P are all constants. And so what that means then is that this ratio of volume over temperature is constant. V1 over T1 equals V2 over T2. And this is called Charles's law, and this is the one that we introduced early on. But again, you can always get it from PV equals nRT if you don't remember exactly which one this refers to. So what we're solving for is the new volume after the increase in temperature. So we're looking for V2, which is going to be V1 times the ratio of T2 over T1. And so from here, we just have to plug in the information that we're given. But the only key thing is make sure that temperature is always in Kelvin. In chapter 7, it was always delta T, so Kelvin, Celsius pretty much interchangeable for that difference in temperature. But for absolute temperature, when it's just T by itself, it needs to be in Kelvin for any type of problem. So we're going to use that. So we have the volume is 253, but then we need to convert the temperatures into Kelvin. So T1, the initial temperature is 24 degrees Celsius. We already did this once earlier for a different problem, but we're going to add 273 to get it to Kelvin, so that's 297. T2 is 86 degrees Celsius. Also have to add 273 to get it to Kelvin, so that comes out to 359. And now we can plug in the two temperatures, T2 on top, 359 Kelvin, over T1, which is 297. And this comes out then to 306 milliliters. So the temperature increases, so does the volume. That should make sense conceptually. And then numerically it works out as long as we have the temperatures in Kelvin. And we can put the volume in directly in milliliters because the two temperature terms, the units cancel. And so whatever volume unit we use here is going to then be the unit that we get for our answer. We wanted it in milliliters for this problem to identify choice C as the correct one. Okay, any questions on that? Okay. So for number 11, then we have another gas law problem that's just a little bit more complicated. So we have a steel tank, which means it has a fixed volume. So volume is constant. It's filled with 126 grams of nitrogen at 298 Kelvin and has a pressure of 235 kilopascals. What will the new pressure be if we add 96 grams of nitrogen and the temperature cools to 273? All right, and we want the answer in kilopascals. So in this problem here, PV equals nRT is always going to be our starting point when we're relating properties of gases, pressure, volume, number of moles, and temperature. What we're doing in this case is we're trying to calculate the new pressure. So pressure is going to be changing in this problem, and we're adding gas to the cylinder. So we're starting with a certain amount, adding more, so number of moles is going to change. Then we're also changing the temperature. We're going from 298 to 273. So all three of those are changing, and there is no prescribed gas law that relates pressure, number of moles, and temperature, but we can derive it from P equals nRT. Yep.
Before you get too far in on this one, on the last one, how did you decide which is T1 and T2?
So it depends on how you define V1 and V2. So I said that the initial volume is V1 and the initial temperature is T1. So those are the two that go together.
Okay.
And then I defined this as T2, and then V2 is going to be what we're solving for, the new volume that's associated with that. If you switch 1 and 2, that's okay, but just make sure that the corresponding temperatures and volumes go together with each other. So you could have called this V2, T2, and this T1, but you just have to make sure you set up so however you set up, it'll be fine. And then same story here. We can define our starting and ending point sort of arbitrarily, but I'll say that initially this is our temperature and pressure, and then we're going to get the number of moles from that, and then we'll say the new conditions, the new temperature, and the new number of moles is our final conditions. All right, but in this problem here, we have those three things changing, so we move them all over to one side. P over NT is equal to R over V, which is constant. Volume is the only thing that's constant here in addition to R, which is always constant. So that allows us to derive a relationship that this ratio, P over NT, is going to stay constant, so that P1 over N1 T1 equals P2 over N2 T2. And then what we're solving for here is the final pressure P2. So P2 is going to be the initial pressure P1, then we're going to have the ratio N2 over N1, and then the ratio T2 over T1. And then we just start plugging things in. So the initial pressure, we want the final pressure to be in kilopascals. The initial pressure is also in kPa, so we're just going to use that number directly. R dropped out, so we don't really care what our pressure and volume units are anymore. And then the ratio of N2 over N1. So for this problem here, we're not telling you directly the number of moles, we're giving you masses of each. So we have N1 is going to be the number of moles that corresponds to 126 grams of N2. So we divide by the molar mass of N2 to get that into moles. So 28 grams per mole for N2. So 4.50 moles is the initial amount of N2 that we have. And then for the final number of moles, N2, we have that much that we started with, and then we added to that another 96 grams. Remember that the number of moles is not how much you're adding, it's the total amount that you have in that situation. So we started with 4.5 moles, we added more, which is 96 grams, we have to add that together. So 96 grams is added. So we divide that by 28 and add it to the original which comes out to 7.93 moles. All right, so this is N2, this is N1, so those go into here, 7.93 moles divided by 4.50. And then what we're going to have for T2 and T1, these are already in Kelvin, so just make sure we keep which one is which. So T2 is the final temperature, which is 273. T1 is the initial, which is 298, no conversions needed. And so all that together gives us 379.4 kPa. So we added more nitrogen, which would raise the pressure, but we also lowered the temperature, which dropped it somewhat, and the total ends up being 379.4, which is still higher than the original. So again, any combination of these three variables, pressure, volume, or four variables, sorry, pressure, volume, number of moles, and temperature, we can always derive relationships between them. And this is not a specific named gas law, but we can figure out what it is from PV equals nRT, and then we just have to set the final initial conditions equal to each other. All right, questions? All right, let's keep going then. All right, this one here is a gas stoichiometry problem. So we have NO and Cl2 react to form NOCl. We have 32.5 liters of NO, 21.2 liters at STP for Cl2. How many liters of our product form? So in problems like this, first it's a stoichiometry problem, so we're figuring out how much product forms from given amounts of reactants. We need a balanced equation. So NO and Cl2 react to form NOCl. Not a terribly difficult one to balance, but we need a 2 there to balance chlorine, and then a 2 there to keep nitrogen and oxygen balanced. These are all gas phase reactants and products. That's important for this problem. Now, one thing that I always forget to cover in class, and then I kick myself every semester for not doing it. This, which you saw it on the homework assignment, so it shouldn't be a big mystery now, but there's abbreviation STP. So STP means standard temperature and pressure. And it corresponds to 1 atmosphere is the pressure, and 273 Kelvin is the temperature. So whenever you see STP, that tells you that the overall pressure is 1 atmosphere, and the overall temperature is 273. Now, in a problem like this is a stoichiometry problem, we can do it in terms of moles, and that's how we're comfortable with doing stoichiometry. Back in chapter 5, when we first started it, chapter 6 with solution stoichiometry, everything revolved around moles. And so what we could do in this problem, because we know the temperature and the pressure and the volume of each gas, we could use PV equals nRT to go ahead and find moles of each gas. But there is a helpful shortcut on this, which is that from this equation, PV equals nRT, N in number of volume, N in V, number of moles in the volume of each gas, are directly proportional to each other. They're linearly related. And so what that means is for gas phase reactions, we can do it directly in volume units. We can interpret this equation as 2 liters of NO reacts with 1 liter of Cl2 to form 2 liters of NOCl, and we can just use the given volumes as the quantities because volume and number of moles are directly proportional for gas phase substances. So what that means we can do then is we don't have to do any conversions. We could use PV equals nRT and find number of moles of each and go forward, but we actually don't have to do that, and it saves us a lot of time if we don't. So what we can do is for each reactant, NO and Cl2, we can find the stoichiometric ratio, because this is a limiting reactant situation because we have amounts of both. We have the volume of NO and the volume of Cl2, so to figure out which one the limiting reactant is if we're going to calculate how much product forms, but we can just use the volumes directly instead of converting to moles because those two are directly proportional to each other. So for NO, the stoichiometric ratio is just going to be, in volume terms, the amount that we have, which is 32.5 liters, divided by the coefficient from the balanced equation, which is 2. So that comes out to 16.25. And then for Cl2, we're reacting 21.2 liters, and the coefficient for Cl2 is 1, and so that stoichiometric ratio in terms of volume comes out to 21.2. So this one is clearly smaller. 16 is smaller than 21. So that tells us that NOs are a limiting reactant. And so then we can use that amount of NO to calculate how much NOCl would form. We're looking for the volume of NOCl that forms in liters. We have 32.5 liters of NO. And then from the balanced equation, we're going to form 2 liters of NOCl. Again, for gas phase reactions, you can interpret coefficients as volume ratios as well. So 2 liters of NOCl are going to form for every 2 liters of NO that react. Both have coefficients of 2. So you end up getting the same number, 32.5. So you can just enter that number in, 32.5, as your answer. So for gas phase reactions, you can convert to moles if you're more comfortable doing that, but it would require you to use PV equals nRT a few times to do that first, and then once you get your answer in moles, go back to volume using PV equals nRT again. So it's just a lot of extra sort of closed loop, work that you'd have to do to get to that point. Okay, any questions? All right, so that's gas stoichiometry for you. And then another concept that we dealt with a bit in this section of the course was the density of gases. In relationships between density and the ideal gas equation. So here we have a 250 milliliter gas bulb filled with 0.379 grams of a gas at STP. And again, STP tells us that we're going to have 1 atmosphere of pressure and 273 Kelvin for the temperature. So which of these is most likely to be the gas? So there's going to be sort of 2 ways that we can do this problem here. So one would be to sort of set up the density equation where we start with PV equals nRT as we always do in this chapter. We rewrite number of moles in terms of mass divided by molar mass. And then we plug it in and say that pressure times volume is equal to mass over molar mass times RT. And then density is mass divided by volume. So we just take mass over volume on one side, and we get pressure times molar mass over RT on the other. So we could set it up this way, where we just put the mass and the volume in that we're given to calculate the density of the gas, and then set it equal to pressure times molar mass over RT. Basically, we're trying to identify which gas it is, and we're going to do that by finding out what the molar mass is and figuring out which of these is closest to that. So that's one way to do it. The other way to do it would be to recognize, and it's really the same concept, just thought about slightly differently. The definition of molar mass, as we said a little bit up here, just rearranged form of this, molar mass is mass divided by number of moles, N. So what we could do is use PV equals nRT to find number of moles and then divide by the given mass. So there's two different ways of approaching this. I don't have a preference for which one. I don't know, does anybody have a preference for each of these? A, B? Which way do you usually do it? I forget.
I think I used the PV equals nRT at one time, but I think you had showed me like the other way to do it. Okay,
so let's do the second way, just in case you forgot the density equation or that we even had it. So if you don't remember that we have an equation for density, but you remember that we have PV equals nRT, and you remember what the definition of molar mass is, then we can use those two together. So our molar mass is mass divided by number of moles. We're telling you that we have 0.379. And then we're going to divide that by the number of moles that we're going to get from PV equals nRT. So the number of moles is going to be PV over RT. And because we're at STP, the pressure is 1 atmosphere. The volume of the gas is 250 milliliters, which is going to be 0.250 liters. We need it in liters for the ideal gas equation. R is 0.0821. And then the temperature at STP is 273. All right, so I need to calculate this out because I didn't initially do it this way. So give me 1 second and hopefully not make a mistake this time. So I got 0.0112 with some degree of rounding. All right, so that's the number of moles that I got. So this is what we can do. We can use P equals nRT to find the number of moles. We have the mass, we have the moles. The ratio of those two is the molar mass. So we divide the two. And again, possibly a little bit off because of rounding, but I got something like 34.0 grams per mole for this. Okay. So that's the molar mass that we get, and we just have to figure out which of these four substances has a molar mass that's closest to 34, and that's going to identify which one it is. So for pH3, if we calculate molar mass, we have to move these out of the way, sorry. For pH3, the molar mass is about 34. For SO2, the molar mass is 64. For N2, the molar mass is 28. And for argon, the molar mass is just the atomic mass off the periodic table, which is 40. And so the one that's clearly closest, we got pretty much exactly 34 grams per mole, and that matches up best with phosphine pH3. Okay, so in problems like this where you're identifying an unknown gas, this is the most common way you do it. You're going to use the density equation or a combination of PV equals nRT with the definition of molar mass. Either of those two approaches will get you to the unknown molar mass. So you either use the density equation and solve for molar mass, or you do it in two steps like I did, which is find the number of moles, divide mass by moles. Either way will get you the same molar mass, and then you compare to what you're given as answer choices to find the one that works. All right, questions? All right, number 14 here we have a tank containing 3.25 atmospheres of nitrogen with a volume of 9.3 liters, and then we're connecting it to a tank containing 5.33 atmospheres of O2 with a volume of 15.2. When we open the valve connecting the two tanks, which allows the two gases to mix. What is the final pressure, assuming that there's no chemical reaction occurring and that the temperature remains constant? So this is sort of an application of Dalton's law, where we have a mixture of two gases, and the total pressure is going to be the sum of the pressures, the partial pressures for each individual gas in the mixture. So whenever we have a mixture of two or more gases, we know that the total pressure is equal to the pressure of the partial pressures of each gas that's mixed together. And so what we need to do is we need to figure out what these partial pressures are after the gases are allowed to mix together. Before they mix, we know that the pressure of nitrogen is 3.25 and the pressure of O2 is 5.33, but we can't just add those together because once we mix them together, the volume changes. And the volume changes for each gas, their partial pressures are also going to change. We have to figure out what those are first. So for each gas, what we're going to do is set up sort of a Boyle's law problem, because for each gas, the volume is changing when we mix them together. Once they mix, they're able to occupy the total volume, and then we have to figure out what the new partial pressure would be. So for each gas, we're going to start with PV equals nRT. Number of moles and the temperature for that gas is all staying the same, so these are going to be constant. Which means that for each individual gas, nitrogen and oxygen, P1V1 equals P2V2, so we're going to again set it up as Boyle's law. So what we're going to do is we're going to find the final pressure, P2, for each gas, which is going to be P1 times V1 over V2. So for nitrogen, the pressure after mixing, the partial pressure after mixing, is P1, which is the initial pressure, times V1 over V2. The initial volume for nitrogen is 9.3 liters. And then once we mix the two gases together, they're going to occupy the total volume that they have available to them. So for both gases, V2 is going to be the volume of the first tank, which is the nitrogen tank, 9.30, plus the volume of the second tank, which is 15.2, which comes out to 24.5 liters. So once the gases mix, they occupy the entire 24.5 liters, the sum of the volumes of the two individual compartments, and that's going to be our final volume for both. So for N2, V2 is 24.5 liters, and that means its partial pressure after mixing will be 1.23 atmospheres. And then for O2, its partial pressure after mixing, P2, is going to be its initial pressure, which is 5.33, times its V1 over V2. So the initial volume for oxygen was 15.2 liters. Final volume is the same for both gases once they mix, 24.5. And so the partial pressure for oxygen after mixing is 3.31 atmospheres. So now we have the two partial pressures after mixing, 1.23 and 3.31, and we just need to add those together to get the total pressure. So 1.23 atmospheres for nitrogen, 3.31 for oxygen. It doesn't matter that the two separate gases, the pressures are still additive, and we get 4.54. All right, so this is a pretty typical gas mixing problem, which combines the ideal gas equation, figuring out the new partial pressure after mixing, with Dalton's law, which states that the total pressure is just the sum of the partial pressures. All right, any questions? Let's keep going then. All right, the next couple questions deal with sort of the last part of chapter 8, which is the kinetic molecular theory, the behavior of gases at the molecular level, and especially things like the average velocity, kinetic energy of gas molecules, things like that. So this one deals with effusion. So we have a 2-atmosphere sample of N2 effusing through a small opening. That just means leaking. And it takes 2 minutes to do this. If the sample of an unknown gas under the same conditions takes 3.9 minutes to, sorry, it should be effuse. I keep messing that up. They're both effusing. What is the molar mass? Whether it's diffusion or effusion, you're going to use the same equation anyway, so that doesn't matter. The standard form of the equation is that the ratio of the rates of diffusion or effusion, so for nitrogen over the unknown gas, which we'll call X. Again, it doesn't matter which order you write these in, but the key is if you're comparing rates of effusion, it's going to be inversely related to the square root of the molar masses. So on the right side, you have X on the top and N2 on the bottom. But in this problem here, we're not talking about how fast it takes to effuse. We're talking about the amount of time that it takes to effuse. So basically, if something is effusing faster, it's going to take less time and vice versa. And so that means the form of the equation we use that involves the times, the time for nitrogen over the time for the unknown, that's going to be directly related to the square root ratio of the molar mass. So we're talking about the time that it takes. We're going to have N2 over here on the top. So basically, we need to flip one side of the equation to get it to work in units of time. So we're looking for the unknown molar mass. So this down here is going to be our unknown. And so now we just have to plug in the numbers and solve. So the time that it takes for N2 to effuse is 2.0 minutes. The time that it takes for the unknown is 3.9. It took longer to leak, so that means it's moving slower, which means it's a heavier gas. So it should be bigger than the molar mass of nitrogen. And then on the right side, we have the molar mass of nitrogen, which is 28.0. And then we have on the denominator the unknown molar mass for X. And again, I'll skip the algebra unless anybody has any questions on it. We're going to square both sides, cross multiply, solve for this unknown molar mass, which comes out to 106 grams per mole. All right, and again, it should be bigger than 28 because it's effusing slower. It's taking longer to leak out. Heavier gases move slower. And so choice B works. C and D we could have eliminated because they're both smaller molar masses. But the one that numerically works out is choice B. All right, questions on that question or that topic? All right, so anytime you see effusion, diffusion, this is the equation that should come to mind. And you're just comparing rates or times that it takes, and that's going to be how you'll, in this case, get the unknown molar mass. Okay, for number 16, we have sort of a conceptual question about ideal gases. We want to know which of the following statements about ideal gases is false. In a mixture of two gases A and B, the total pressure depends only on the total moles of A and B, not their identity. So this one is going to be true because, again, the equation PV equals nRT, it doesn't matter what gas you have, it just matters how much you have. And that's true whether it's a single gas or a mixture. So if you have a mixture of gases, kind of like the problem we did two pages ago, if you want to find the total pressure, all that matters is the total amount of gas you have, not what they are, not whether it's a mixture or anything like that. So that one's going to be true. For choice B, samples of helium and oxygen at STP have the same average kinetic energy. So this is where it's important to keep straight the difference between kinetic energy and average velocity. They're related to each other, but they have slightly different dependencies. So we're talking about kinetic energy. Average kinetic energy only depends on the temperature. And so it doesn't matter what gas you have, if they're at the same temperature, they're going to have the same average kinetic energy. So if we're talking about two gases that are both at SCP, meaning they're both at 273 Kelvin, they will have the same average kinetic energy. It doesn't matter what gases they are. So kinetic energy only depends on temperature, so this one would also be true. If we go to choice C though, samples of helium and oxygen at STP have different average molecular speeds. O2 is higher. So at a given temperature, that we said they have the same average kinetic energy, but that kinetic energy is equal to 1/2 times the mass times the average of the square of the velocity. And so because the kinetic energies of these two are the same, the one that has the higher mass is going to have the smaller velocity and vice versa. As we talked about, if they're at the same temperature, heavier gases on average move slower, lighter gases move faster. And so for helium and oxygen, helium has an atomic mass of 4, oxygen has a molar mass of 32. Oxygen is much heavier, so its average speed should be lower. So this one is going to be false because that should be lower instead of higher. All right, so this is identified as a false statement. Then we have to see about choice D as well. Deviations from the ideal gas law are smallest at high pressure and low temperature. And again, this is exactly the opposite of what it should be. Deviations are going to be smallest when you have the gas molecules as far apart as possible and moving as fast as possible. So when we're talking about deviations from the ideal gas law, the smallest deviations occur at low pressure, large volume, those two are related to each other, and then high temperature, where the gas is moving as fast as possible. So deviations will be smallest at high pressure and low pressure. That's when they're going to be largest. So this one is also false as well. Written again in the opposite sense that it should be. So both choices C and D are false statements. That would be the correct answer that we would pick here. All right, so those are a review of some of the key concepts involving ideal gases as well as deviations from the ideal gas law that occur under certain conditions. So anything you want to clarify on that? All right. The last 4 questions on this deal with the newest Chapter 9 material, but again, it's just the first 4 sections of Chapter 9. So it's mostly going to be intermolecular forces, liquids, and phase diagrams. Those are kind of the key topics from that part. Anything else that we dealt with solid structures and solid materials is all going to be on the final exam only. So this first question here deals with which intermolecular forces are present in SF4. So one thing to keep in mind is that for London dispersion forces, everything has London dispersion forces. So it doesn't matter what kind of substance it is. If it has one or more electrons, which every substance does, it's going to have dispersion forces. So London dispersion forces is always present. Now it's also true, although it's not really relevant to this question, but it's also true that London dispersion forces are the weakest intermolecular forces. So if you have other types of intermolecular forces in addition, they're going to typically be more important. The strongest forces are the ones that are going to be the ones that matter the most in terms of determining the properties. And so it is important to consider other types as well. In this problem, we want to know, is there anything else besides London dispersion forces? And that's going to be determined by the nature of the substance. So if we have a covalent compound like SF4, essentially there's 3 types of intermolecular forces. London dispersion forces, which we'll always have, and then the other 2 are dipole-dipole forces and hydrogen bonds. Dipole-dipole forces will only occur if the molecule is polar. Hydrogen bonds will only occur if it has hydrogen bonded to oxygen, nitrogen, or fluorine. This doesn't have hydrogen at all, so there's no way this could have hydrogen bonding. So we can eliminate that, although it's not one of the choices anyway. But to determine if it has dipole-dipole forces, we need to figure out if it's polar or not. So this is going to be a review of Chapter 4, but it is important for this part to understand polarity again, because another consequence of polarity is the type of intermolecular forces that would be there. So we have to count electrons and draw a Lewis structure and then figure out if it's polar or not. So sulfur is group 6. Let's review that quickly. Sulfur is group 6, so it has 6 valence electrons. Fluorine is group 7, so each one has 7. So we count electrons to make sure we're using the right number. So we have 34 valence electrons for SF4. So when we draw the Lewis structure of SF4, after completing the octets on fluorine, so 8 electrons each for the fluorine atoms, 2 from the bond, 6 more as lone pairs. 4 times 8 is 32. We have 2 more let go on the central atom then. All right, so this is an AX4E structure, and whether we remember this geometry or not, anything that has 1 lone pair on the central atom is always going to be polar. That's an important shortcut we talked about back in chapter 4. So with 1 lone pair on the central atom, you know it's polar. Because it's polar, it's going to have dipole-dipole forces as well. Let me not circle that, it's confusing. So it has both London dispersion forces and dipole-dipole forces. We don't want to count covalent bonds because these are not intermolecular forces. This compound does have covalent bonds. It's 2 nonmetals, sulfur and fluorine, but that's not classified as an intermolecular force. It's classified as an intramolecular force, which is not relevant to this part of the course or to this particular problem. So the correct answer would be 2 of these. It has London dispersion forces just like everything else, and because it's polar, it has dipole-dipole forces. Choice B would not even be considered because it's not an intermolecular force. All right, questions? Yeah.
Why is it not in IMF?
So intermolecular force, IMF, means between molecules. So that refers to the forces that would hold collections of molecules together. The covalent bond holds the atoms together in a single molecule, but is classified as an intramolecular force. So it's intra versus inter. So we don't usually use the word intramolecular force because it's confusing anyway. But when we talk about IMF, we're talking about the weaker forces that hold molecules together as a collection, not the forces that hold the atoms together in a single molecule, which is what the covalent bonds would do. All right, any other questions? All right, last 3. So this one is another one that deals with intermolecular forces, but now talking about which properties, how they depend on it. So which of the following does not increase with the strength of intermolecular forces? So this one I'll just talk us through. So both of the phase change temperatures, the melting point and the boiling point, remember that what's happening with melting is you have a solid substance that's held together by intermolecular forces, and to melt it, you have to break some of those forces to get the molecules to start moving around. So the melting point will increase if the intermolecular forces are stronger, because it requires more energy to break those forces apart. And then similarly for boiling, which requires even more energy, because when you boil a substance, you have it in the liquid phase, there's still intermolecular forces holding the molecules together, although they're now in motion. But then to boil it, you have to completely separate them from each other. So in that case, you have to break all of the intermolecular forces. So both of those increase when the intermolecular forces get stronger, because it requires more thermal energy to break those forces apart and get the molecules moving and then eventually get them into the gas phase. So both of these increase with the strength of the intermolecular forces. That's both phase change temperatures. The next 2 are properties of liquids. So viscosity is how thick the liquid is, and that one also increases with the strength of intermolecular forces, because how readily the molecules flow in a liquid, how thick it appears as a liquid depends on how strongly they're held together. So if you have stronger intermolecular forces, you tend to have a thicker, more viscous liquid. So that one also increases. And then surface tension, which is basically that upper bound that a liquid surface has, where basically all the forces are pulling down on those top molecules and keeping them sort of rigid at the top. That's also going to increase if the intermolecular forces get stronger. So all of those key properties of a liquid, melting point, boiling point, viscosity, surface tension, they all increase with strength of IMS. The last one, though, which is ideal gas behavior, this kind of combines, again, Chapter 8 and Chapter 9 concepts. For ideal gas behavior, we assume that the gas molecules have no interactions, no IMFs at all. So if you make those IMFs stronger, that's going to make them behave less like an ideal gas and more like a liquid, or more like a real gas, if it would be, I can say it that way. So this one is going to be the only one that doesn't increase. If you make the intermolecular forces stronger, it's going to behave less and less like an ideal gas, because ideal gases, you assume that there's no intermolecular forces. That's the sort of ideal case. All right, so any questions on that one? All right, last 2 then. This is sort of the only numerical problem that we have for Chapter 9. And so what we have in this case is we want to know how much heat must be added to convert 25.3 grams of dry ice, solid carbon dioxide, at minus 78 degrees Celsius to gaseous CO2 at 25 degrees Celsius. So this is a pretty typical, heating curve problem where we have different phases involving both phase changes as well as warming the substance up. The only difference here is that because we're talking about carbon dioxide, we don't have melting and boiling, we have sublimation, which is directly going from solid to gas. But that doesn't really change how we approach the problem, because basically what we're going to have is one phase change to consider, which is directly from solid to gas, that occurs at this temperature and has this enthalpy change, heat of sublimation, associated with it. And then we have the specific heat to warm it up. So what we're doing in this case is we're starting in the solid phase exactly at the sublimation temperature. And so when we first start putting heat into this, it's going to sublime into the gas phase. So that's going to be our first step. Is sublimation. So we're right at the phase change temperature. Minus 78.5 is our starting point. So as soon as we start warming it up, that's what's going to happen first. It's going to sublime into the gas phase. And so for this, the sublimation, the amount of heat required is going to be just the moles of substance multiplied by the heat of sublimation. Now for the phase change enthalpies, you do have to be a little bit careful with units. Sometimes they're given per mole, sometimes they're given per gram. There was a homework question that had enthalpy changes in kilojoules per gram, and some people didn't catch that, and then multiply by moles instead. So look at what's given to you first. This one is given per mole, so that means we're going to use the moles of CO2 multiplied by that number to get the amount of heat associated with it. So we have to calculate moles of CO2 that we have, because it's given in grams here again. So it's going to be 25.3 grams. And then the molar mass of CO2 is 44.02. So what I got was 0.575 moles. So that's how many moles of carbon dioxide we have, and we're going to multiply that by the heat of sublimation to figure out how much heat is required to sublime that much carbon dioxide. So 0.575 moles multiplied by the heat of sublimation, which is 26.0 kilojoules per mole, tells us that we need 14.95 kilojoules to sublime that amount of CO2. So that's step one. Once we've done that and we're in the gas phase, we're at minus 78.5 degrees Celsius still. The phase change is a constant temperature. But then we said that we're going to warm it up all the way to 25 degrees Celsius. So the second step is going to be the amount of heat that's required to warm it up from the phase change temperature all the way to 25, which is our stopping point in this case. So our second step is we're going to heat it from the phase change temperature, minus 78.5, where it first becomes a gas, up to the final temperature of 25 degrees Celsius. And anytime we're just changing the temperature but not changing the phase, it's just going to be back to MC delta T that we talked about beginning in chapter 6. So in this case, the heat capacity is given per gram, so we're going to use that mass value this time, 25.3 grams. Specific heat capacity of gas phase CO2 is 0.819. And then the delta T, we have final temperature is 25 degrees Celsius. Be a little bit careful with signs here. Minus the initial temperature, which is minus 78.5. So our total delta T is somewhere around, what would that be? 100 some degrees Celsius, because we're going from minus 78.5 all the way up to plus 25. So the difference there is big. So this comes out, this answer is going to be in joules, because that's what our heat capacity is in. So 21.45 joules. We want to add them together. I guess we didn't specify a unit here, but typically it'll be in kilojoules. So we're divide this by 1,000 to get into kilojoules. All right, and so that means the last step to do is just to add them together to get the total amount of heat. So the total amount of heat is going to be the amount that it took to sublime, which is 14.95. Plus the amount that it took to warm it up, which is 2.145, which comes out to 17.1 kilojoules. And again, I didn't set this up exactly like a Blackboard problem, because I didn't specify units or decimal places or things like that, but this would be the correct answer, however you're supposed to enter it in. All right, So in problems like this, you just have to keep track of which phase changes are going to be involved. That depends on the starting and ending temperature. And every time you get to a phase change temperature, you need to account for that. And then any warming stage to get to that point would be MC delta T. Yep.
Can you explain what the second equation is again?
This one here, MC delta T. So this is what we learned back in chapter 7. This is just the amount of heat that's required to change the temperature of a substance. And so whenever you're going in the same phase, so from minus 78.5 to 25 degrees Celsius, it's still all in the gas phase, and you're just warming up the temperature. So you're just going to use that equation to figure out how much heat is involved with that, where M is the mass of the substance, C is the specific heat capacity, and then delta T is the change in temperature that you're going through. All right, anything else? All right, so last one deals with phase diagrams. With phase diagrams, there's a lot of different things we can ask you, and I went through kind of a exhaustive list of those different things in class, where you could ask for which phase is present at a certain point in the diagram, where does a phase change occur, where's the triple point, critical point, all these different things. And this one covers a few of those things, so we'll kind of get a review of that here. So we want to know which of the following is a correct statement about the phase diagram below. Okay, so the first one here, liquid can exist below 0.6 atmospheres. So to figure out if that's true or not, we just draw a line through 0.6 atmospheres, and we see that this is our solid here on the left, liquid in the middle, gas on the right. Now what we notice is that our triple point here occurs at 0.6 atmospheres. Liquid doesn't exist below the triple point, so anywhere below 0.6 we see is only the gas phase or the solid phase. There is no liquid below 0.6, because that liquid part of the diagram ends at the triple point, which is right there. Anything below 0.6 is only solid or gas. This one's going to be false. Looking for the correct or the true statement. At point A in the diagram, only the gas phase is present. Well, point A is all the way to the left, which is solids. This one is also false. It's helpful to label those, or at least keep it in your mind as you're starting. Point E in the diagram is called the triple point. So remember, the triple point is this one here, where they all three come together. The point where the liquid gas line ends is called the critical point, not the triple point. So this one is also wrong. All right, and then finally, at point B in the diagram, liquid and gas phases are both present. So this one is going to be true, because anytime we're on the liquid gas line, let me highlight that in a different color. So if we're on this line here, which separates the liquid and gas regions, if we're right on the line, which is true for point B, that means both liquid and gas exist together. That would be basically where that phase change occurs between liquid and gas. And so this one's going to be the one that's going to be true, because anytime you're on a phase change line, those two phases that are bounding that line, in this case liquid and gas for point B, those are both going to be present, and they're going to be converting between the two as you either continue to warm it up or change the pressure from there. All right, so that one's our true statement. All the rest are false. Any questions on that or anything else? All right, thanks for coming, or thanks for watching if you caught this online, and good luck with your exam next week. If you have any last questions, I will be around and available by email as well. Stop this real quick.